Okay, here's a drawing of a rocket at two different instants in time. In this first instant, the rocket has not yet expelled some gases. In the second instant, it's now expelling gases that it has ignited. So we'll say that in the first picture, this thing has a mass m plus delta m, and is traveling at a velocity v. In the second picture, it's my neighbor's knocking, the expelled gases have this mass delta m, and the rocket plus whatever gases are left over has a mass m. And this rocket has sped up. It has a new velocity v plus delta v. And these expelled gases are exiting this rocket at an exit velocity ve that's relative to the rocket itself. So the velocity of those gases is the rocket's velocity minus that exhaust velocity, not exit velocity, exhaust velocity. Okay, so let me be clear about what these symbols mean. M is the mass of the rocket plus fuel. Delta M is the mass of the expelled gases, expelled fuel. V is the rocket's velocity relative to some fixed point, like relative to planet Earth. Delta V is that change in velocity. And VE is the exhaust velocity, the velocity of the expelled gases relative to the rocket itself. Okay, now that we've got all of our symbols defined, we can do conservation of momentum analysis. So here's our initial configuration. We have the initial mass is m plus delta m. The initial velocity is v. And then in the final situation, there's kind of two separate objects. There's the gas itself, which has mass delta m, and it has velocity v minus v exhaust. And then there's the rocket. It has mass m, and it has velocity v plus delta v. All right, now we can do some algebra here. A lot of these things cancel. Notice we've got mv we've got delta m times v, and those terms all cancel. So with a little bit of algebra, we get mass times delta V equals mass of the gases times V exhaust. And we'll note that delta little m is the same thing as negative delta big M. As this rocket loses mass from the fuel, that is the same as the gain in mass of the exhaust gases. So this equation looks like M delta V equals minus delta M V exhaust. And now you can write this in the form delta V over V exhaust equals minus delta M over M. We're just worried about motion in one direction, so we can get rid of those vector signs. And now by the magic of calculus, you can solve this differential equation and you get the result that the change in velocity, or V final minus V initial for any two instants in time, equals the exhaust velocity times the natural log of the initial mass of the rocket divided by the final mass. And now this is the rocket equation. Next we'll explore some applications